In this video series, we're going to be discussing the fundamentals of logic and writing proofs. It is worth noting that the majority of the content here will be derived from the notes that I took from the ME 564 Linear Systems Theory course taught at the University of Michigan by Professor Anouk Girard in the winter 2018 semester. So the goal of this series is to establish fundamental understanding of how to write and/or interpret proofs. Now, why do we care about proofs? Well, to win argument, of course, but more specifically, or I guess more accurately, to show that stated assumptions logically agree to some sort of conclusion. You see, when it comes to proving an argument, it's not enough just to show an example or even multiple examples of where your statement holds. You need to be able to prove that your statement holds in every single case, and that's why we like proofs. Because proofs demonstrate that a statement is true in all possible cases. You can use proofs in just about any discipline, but we on this channel will like to focus on engineering and robotics. But it should be noted that you can take what we've learned in this video series and apply it to just about anything that you want. So what does a proof look like? It's a series of statements, or so-called propositions, that are listed one after the other, where each statement can be inferred from a previous statement. And the final statement in the proof is called the conclusion. Don't worry too much about the terminology here, as we will be diving more into this as we progress in this video series. So a high-level depiction of what a proof actually looks like would be something like this, where you start with an argument, which is the thing that you're trying to prove, and then you draw out a 3-column table. And the first column is just the step number, and these are just the number of steps that it takes for you to prove your argument. In the middle column is the propositions, and these will just be the series of statements that you list one after the other. Where in the third column, you justify, because it's the justification column, and here you list out the justification of the proposition in the corresponding row right next to it. And then you typically end a proof with this symbol, this little square symbol right here. It should be noted that I say that this is the high-level depiction proofs that are with training wheels, because typically when you see a proof, you probably won't see tables like this. In fact, you might just see something like just this middle column, essentially. But since we're just learning how to do proofs, we're going to be working towards this depiction of it, so that we're able to see and justify everything that we're doing. So now that we know where we're going, let's actually get there. In this first video, we'll be talking about the basic of logical operators and truth tables. So first, a definition. A proposition is a statement that can either be true or false, but not both. For example, these are some examples of propositions. I am a student. It is Friday. Detroit is in Michigan. These are all propositions because these are all statements. Some non-examples of propositions will be this. Pay attention. This is not a proposition because this is actually a command, not a statement. 365 days a year. That's also not a proposition because this is a sentence fragment. In fact, you need more information here. What time is it? This is also not a proposition because this is actually a question, not a statement. So a proposition is a statement that can either be true or false. You can represent a proposition via a letter, and most people commonly start with the letters P and Q, but really you can use any letter that you want. So for example, P can equal to I am a student, Q is equal to it is Friday, and so on. In this way, you're able to essentially consolidate your writing. So rather than writing out entire statements, you can just represent the statement with a letter, which comes in handy when it comes to writing proofs. So here are some basic logical operators that we're going to be dealing with. The first one is the not operator that can be depicted by either of these two symbols right here. In this video series, you'll typically see me using this tilde symbol. However, in some of the examples that I show and some of the contents that I show, I might be pulling directly from my lecture notes from the ME 564 course. And in those notes, you'll typically see this symbol. Both these symbols mean the exact same thing, in that they both represent the not logical operator. The second symbol is this caret symbol, and this represents the and logical operator. And finally, the last operator I want to talk to you about is the or operator, depicted by this symbol right here. To illustrate what these operators look like and to understand what they actually mean, I'm going to show you how to use them using a truth table. So let's start simple with the truth table for the not operator. Well, first we're going to actually need a proposition, something that we can apply this not operator to. So let's say give it the proposition P. Now we want to list out every possible case that P can be. And as I stated before, propositions can either be true or false, so this is easy. We'll just say T for true and F for false. In the next column, we're going to be actually applying the not operator on this proposition P. And so this is actually pretty straightforward. So in the case when P has a truth value of T, the not operator on this proposition P would be false, yield a false. And in the case when the proposition P holds a truth value of false, the not operator acting on this proposition would make the statement to be true. And now let's go to the truth table for the and operator. Here we're going to actually need two propositions because the and operator is what we call binary. So I have two propositions right here. We're calling them P and Q. And just like before, we want to list every possible combination for these two statements. And as I said before, propositions can either be true or false. So we're going to actually have 4 different cases. So here I'm just listing out all the combinations for P, and like I said, there's only 2, true and false, but you'll notice that I have 2 of each, and that's because we have to consider the Q. And so here I'm just listing out true and false in alternative patterns, and you can see that this yields to us every possible combination, or every possible PQ combination. And now in this last column, we're going to be actually applying the and operator on both of these 2 statements. And it should be noted for both statements need to be true for the and operator acting on the statements to be true. So if we look at this first case where both statements are true, P is true and Q is true, then the and operator on here means that it's going to be true. In the next case, where P is true and Q is false, the and operator acting on here will be false because both statements aren't true or don't have true values of true. In the next case, this is similar. Since the true value for P is false, even though that the true value for the Q is true, this automatically means that the and operator acting on both these statements will have overall true value of false, since both the statements don't have truth. They both don't have truth values of true. And finally, this last case, both of the propositions have truth values of false, which means that the and operator acting on this will yield an overall statement to be false. And finally, the truth table for the or operator. We're going to still need 2 propositions because this is also a binary operator. And so we fill out the table like so. We have our 2 propositions, P and Q, and we're going to fill out all possible combinations as we did it before in the previous case. So this is exactly what we did before. And now we want to fill out this last column where we're actually acting out the or operator. And it should be noted that at least one of the statements need to be true for the or operator acting on the statements to be true. So in this first case, both of the statements or propositions happen to be true, which means that the or operator acting on this will be true. In the next case, P has a truth value of true and Q has a truth value of false. But the or operator acting on here would be true because at least one of the propositions, specifically the P proposition in this case, has a truth value of true. The same thing goes for this next case. The or operator is going to have a value of true because the Q has a truth value of true in this case, even though the truth value for the P operator has a false here. And finally, in the last case, since neither of the propositions have a true value of true, that means that the OR operator acting on this will yield a false. And now I'm going to talk to you about compound propositions. You can write a compound proposition by using any combination of these operators. So, for example, this is an example of a compound proposition. And you can read this as P or Q and not R. An example that's not a compound proposition would be something like this, P not Q. That actually doesn't make sense syntactically. So this is this is syntactically incorrect. So bringing back the example that I showed in the previous slide, it should be noted, or you should remember, that P, Q, and R are all representing actual statements. So for example, P can be like, I have a car. Q can be, I have a truck. And R could be, I have a license. So if you read this with this substitution in, it will be something like, I have a car, or I have a truck, and I don't have a license. Which doesn't really make sense, but I didn't say that a proposition really had to make sense. This is still a proposition because it's still a statement. So implications. This is another logical operator that we need to talk about. An implication is another binary operator that meaning that requires two propositions, and it's noted in this manner, essentially, where you can read this as P implies Q. You can also read it or interpret it in any of these following ways if you're curious, but we're just going to stick with the whole P implies Q, just to keep things simple. And now for the truth table for the implication. So we still need 3 columns here because we still need 2 statements, or 2 propositions. And as before, we list out every possible case or combination for the P and Q. And now we can fill out this this implication column. For the implication truth table, since I typically like to help myself by substituting values for P and Q. So in this case, I'm going to let P equal to I live in Chicago, and I'm going to let Q equal to I live in Illinois. And so with these 2 statements in mind, I'm going to now try to fill out the implication table. So the first case, where both P and Q are true. I live in Chicago implies that I live in Illinois. Yeah, that makes sense. I mean, if I live in the city of Chicago, then that means that I'm definitely in the state of Illinois. So yes, it makes sense that the implication for this would be true. In this next case, we're going to read it, the P value has a true value of, the proposition P has a true value of true, and the Q value Q proposition has a true value of false. And so it's going to be read as, I live in Chicago implies that I don't live in Illinois, which actually does not make sense, right? If I live in the city of Chicago, then I am most definitely in the state of Illinois. So we're going to have to put a false here. In this third case, we have a true value of false for the proposition P and a true value of true for the proposition Q. So we're going to read this as, I don't live in Chicago implies that I do live in Illinois. Well, this can be true. I don't necessarily have to live in the city of Chicago to be in the state of Illinois. I could be, say, in Springfield, Illinois, or I could be in Dearborn, Illinois, or Urbana, or Champaign, Illinois. So I don't need to be in Chicago, so this means that this implication is true. And finally, both of the propositions P and Q have a true value of false. So we'll read this as, I don't live in Chicago implies that I don't live in Illinois. And you'll find that this is also true. I could, say, live in, like, Ann Arbor, Michigan, or, like, San Francisco, California, or what have you. So this is the truth table for the implication operator. And it should be noted that this truth table that we just derived can also be written in this manner. So here, I just essentially shifted this third column to the middle column, and I just left the symbol, the implication symbol, as opposed to having P and Q, P and Q here. So both these tables are the exact same thing, and I can do the exact same thing for the AND or operator that we showed before, namely just shifting that third column to the middle column and just leaving the symbol here. So, fun fact. you can actually define the implication P implies Q as not, in parentheses, P and not Q, close parentheses. You know what? Let's prove it, because I don't think you actually believe me. And we're going to prove it using a truth table. So this is the argument that we're making. We're saying that P implies Q is equivalent to not, in parentheses, P and not Q, close parentheses. So let me just rewrite that out here. This is the exact same thing. I just spread out the letters so that I can draw the lines of my truth table. And you'll see in this column right here, this is the equivalency column. We want every truth value in this column to be true, because if all the truth values in this column are true, that means that we would have proven the equivalency of the two propositions on both sides of the equality, or equivalency, I should say. So let's start off by looking at the left-hand side of the equivalency. And you see, this is exactly the implication. This is just going to be simply the implication truth table that we saw before. Namely, that we have two propositions, P and Q. So we start off with listing out every possible combinations that P and Q can be. And so this is the exact same thing that we've done before. And this last column on this left-hand side, the implication column, this is simply just the same truth table that we've derived before. And so nothing's going to change here. This is what we generated before, so that's the values that we place here. Now let's look at the right-hand side of this equivalency. It should be noted that just like in any mathematical operation, we have to pay attention to what the operations that's happening in the parentheses first before we can apply anything that's happening outside the parentheses. So that means we can't quite look at this column right here, this column that has the not operator operating on what's happening on the parentheses. In fact, we have to look at the things that are happening in parentheses first. And now let's actually look at this column first, because this column is simply just the P column. And we already know what P is because we defined it here on this left-hand side of the equivalency. So since we haven't applied it, we're not applying any operator on this in this column. Everything here is simply going to be as what we defined before. So we do exactly that. Now let's look at this column over here. This is not Q. Well, from over here on the left-hand side, we know what Q is, but what is not Q? Well, given our knowledge from the truth table that we derived for the not operator, we can quickly derive what this is. Specifically, whenever the proposition Q has a truth value of true, the not operator acting on Q will yield a false. Similarly, if the proposition Q has a truth value of false, the not operator acting on that proposition will be true. So given that, we can fill out this column like so. And now we can look at this AND column. So here, this AND operator is being applied to P and not Q. And as we remember from before, the results for AND, or a statement that when you apply the AND operator on two propositions, the result will only have a true value of true if both propositions have true values of true. So with that in mind, let's fill this out. Let's look at this first column, or first row. So we have a true value of true here and a true value of false here. That means the AND operator acting on this, in this case, will yield a false. Looking at this next row, we have a true value of true for this side and a true value of true for this side. Perfect. That means that the AND operator acting in this case would be true. The next case, we have a true value of false and another true value of false, in which we're applying the AND operator to, which means that we're going to have a true value of false in this AND operator column. And finally, in the case where we have a true value of false and a true value of true, the AND operator acting on here would yield a false. Awesome. So now we have done everything in the parentheses, which means that we can look outside the parentheses, looking at this this not column. We're going to apply this not operator on the last thing that we filled out in the parentheses, so specifically this and operator column. So when applying the not operator, we need to apply it to this column right here. So let's do that. Not false would be true. Not true would be false. Not false will be true. And once again, not false would be true. Perfect. Now we only have one column left, and that is the equivalency column. And hopefully, to prove our original argument, we need to have everything in this column to have true values of true. So let's see if we get exactly that. We're going to be comparing the columns of this, the last thing that we did, or the last column that we filled out on either side of the equivalency. So on the left-hand side, we'll be comparing this implication column that we have here to the last thing that we did on the right-hand side, which is this not column right here. So let's do this. Is true equivalent to true? Yes. So we have a true value of true here. Is false equivalent to false? Yes. So that has a true value of true. Is true equivalent to true? Yes. So boom, true value of true. And finally, is true equivalent to true? Yes again. Boom, there you have it. We have proven our argument. So remember that a proof shows that a statement is true in all cases. And as depicted by this equivalency column, we have shown that every possible case yields a true value of true for this particular argument, which is exactly what we set out to do. So now let's do some more terms, just to get these under our belt. For the implication P implies Q, the hypothesis or premise is P in this case. The thesis or conclusion is Q in this case. The converse implication is Q implies P. So you notice that we just switched up the order of the propositions. The contrapositive implication is not Q implies not P. Notice that we still have switched the order of the propositions, and then we added the not operator on both propositions in the process as well. This represents the contrapositive. And finally, the inverse implication is not P implies not Q. So here we didn't switch up the order of the propositions. We just applied the not operator on both the propositions. And finally, I also want to talk to you about one last term, and that is the biconditional. And it's represented as follows, where you can read the statement as P if and only if Q. You can also interpret it as any of these ways, but we're going to stick with P if and only if Q, just to keep things simple. And so the truth table for the biconditional would be as follows. So since it's a binary operator, we still need two propositions. So we're going to use P and Q. And now we're going to list out every possible combinations for P and Q as we have done before. So this process hasn't changed. And so now we want to fill out this middle column. So the implication column, the implication of two statements will yield a true value of true only if both of the propositions have the same truth value. So let's look at this. In the case where both P and Q have true values of true, that means the biconditional implication will have a true value of true. In the case where the proposition P has a true value of true and the proposition Q has a true value of false, this yields that the biconditional logical operator will have a true value of false. Similarly, with this third case where the P proposition has a true value of false and the Q has a true value of true, the biconditional in this case would be false. And in this final case where P has a true value of false and Q has a true value of false, even though both of the true values are false, since they have the same truth value, the biconditional will have a truth value of true. You can also write the biconditional P if and only if Q as the proposition P implies Q and Q implies P. In fact, you should prove it to yourselves using the truth table as we've done in our previous example. I encourage you to do this. But this ends the first part of the video series for logic and proof tables, or logic and proofs. In the next video, we're going to be talking about arguments. Thank you.